So if we take a look at this, before we look at predicting products, which is what we're doing today, you have to be able to classify the type of reaction. So if all you're given are the reactants, can you figure out the type of reaction? So again, we have synthesis, decomposition, single replacement, double replacement, and combustion. Those are the 5 types of reactions. So if we take a look at number 1, we have aluminum and chlorine. Aluminum is an element, chlorine is an element. We don't have any compounds. The reason it's Cl2 is because it's one of the diatomics. Make sure you know your 7 diatomics. Right? If it's Bron H. Cliff, those are your 7 diatomic molecules. So anytime you have one of those on their own, it has that too. So here you have a single element and a single element. The only thing that those 2 single elements can do is combine to form something new. So number 1 is synthesis. Now if you did combination instead, that's fine, right? Synthesis and combination are the same thing. That's when you have 2 elements combining to form one thing. Now we're not worrying about predicting the products yet. We'll look at that after we classify. Number 2, we have silver, so a single element, and then we have an entire compound. When you have a single element and an entire compound, single is the key word there. Right, single element and an entire compound, they will replace. So silver will replace hydrogen. This is single replacement. So number 2 is a single replacement reaction. And when it comes to single replacement, we'll look at the activity series. As we look at predicting products, remember the single has to be more active in order to replace the compound. Number 3, so we have carbon, hydrogen. So this is a hydrocarbon. Anything carbon and hydrogen together plus oxygen. So when you have a hydrocarbon plus oxygen, that's like the methane bubbles that we did. So a hydrocarbon plus oxygen is combustion. That plus oxygen, that's when I would stick the match up to the methane bubbles. Right? It'd catch fire, produce CO2 and H2O. Number 4, you have aluminum nitride. You have a single substance. The only thing that single substance can do is break down. And so if the only thing this can do is break down, this is a decomposition reaction. And then number 5, so obviously there's only one that we haven't used, but if we take a look at number 5, we have 2 full compounds. 2 full compounds. We have a metal and a polyatomic, another metal and another polyatomic. So you have 2 ionic compounds. When you have 2 full ionic compounds, that's double replacement. So in a double replacement reaction, your 2 metals will switch places. They'll replace each other. So again, the point of doing this was to classify or be able to figure out the 5 types of reactions. What we're going to do today is we're going to actually look at predicting products. So how can we actually predict the products of each of these reactions? So we're going to look at predicting products, and we're going to do one of each so that you have an example, and then you'll be able to go back through and be able to practice. So if we take a look at Part D. So Part D says complete the chemical equations for the following combination or synthesis reactions. So each one of these sections is split up into each of the types of reactions. So for combination or synthesis reactions, just a reminder, this is when 2 combine to form 1. So 2 combine to form 1. So 2 elements combine to form 1 compound. Right? 2 substances combine to form a single formula. Now, when you create something new, this is the biggest thing. When you create something new, make sure that you crisscross your charges. So crisscross your charges. This is why we want our periodic table. When you form something new, you have to crisscross your charges. So let's take a look at number 6. All right, so we're going to do number 6 together. We have Na plus O2. So again, we know that this is synthesis, yes, because they told us, but also because we have two single elements. We have sodium and oxygen. Those are two elements from the periodic table. The only thing that they can do is combine to form one compound. Now, I need to write just the element. Do not transfer subscripts over. I know this is O2 over here, but that's because oxygen is diatomic when it's by itself. Do not transfer subscripts over. Write each element and then look at their charges from the periodic table. So here's where, if we look at our periodic table, sodium is +1 when it's in a compound. So up above Na, I'm going to write +1. So remember when we wrote chemical formulas, we used our periodic table to figure out charges. Oxygen, when it's in a compound, is -2. So up above oxygen here, I'm going to write -2. So it goes, right, +1, +2. We skip the transition metals. Transition metals can have multiple charges. That's on your polyatomic ion sheet. +3, ±4, -3, -2, -1, 0. So now we wrote these charges up here. Crisscross them. All right, when I crisscross, the 1 comes down after the O, the 2 comes down after the Na. You're just crisscrossing the numbers, not the plus and minus. We end up getting Na2O. Now, if you look at this and you're like, well, yeah, but now, I don't have equal numbers of NAs and O's on both sides. No, that's why we go back and actually balance the equation. Right? We're not going to worry about balancing on these. We're just going to predict the products. So for synthesis or combination reactions, you just write each element, you check the charge, you crisscross. You're forming something new. So that's for a combination reaction. Now we're going to move down. So we're just going to do one in each section, and then we'll come back, right, answer any questions if there's any questions. So part E, this says we're looking at combustion reactions. So again, it says write the chemical equation for the complete combustion. So again, we review, remember combustion is when you have a hydrocarbon plus oxygen. Combustion is always a hydrocarbon plus oxygen. So notice how both of these have a plus. So we're going to have to fill in what else it needs, and then we'll also predict the products. Any hydrocarbon is C and H. Whatever the subscripts are doesn't matter. Octane, that's gasoline. You light gasoline on fire, it's going to go boom. That's a combustion reaction. So whenever it's combustion, it is always plus oxygen. Oxygen is O2 because it's one of the 7 diatomic molecules, right? Braun H. Cliff. So whenever you have combustion, it's always hydrocarbon plus oxygen, and the products are always the same. The products, no matter what you start with, no matter what hydrocarbon you start with, the products are always CO2 plus H2O. Then you'd have to go back in and balance, right? Add your coefficients, but no matter what, it's always CO2 and H2O. We could combust glucose, right? You can actually burn sugar, produce CO2 and H2O. But no matter what, it's a hydrocarbon plus oxygen yields CO2 and H2O. So number 10 is going to look very similar to your number 9, because combustion is always plus O2, makes CO2 and H2O. So then, let's come down to part F. All right, so again, we're just doing one of each. Part F, we're writing for decomposition. So remember, for decomposition, we're breaking the substance down. So break substance down, usually into its elements. So usually into elements. The only other thing I'll put for the decomposition is to pay attention to diatomic molecules. Right, pay attention to diatomics. Remember your 7 diatomic molecules. Bron H. Cliff. Bron H. Cliff are your 7 diatomics. When you have a single substance, like CS2O, this is a single substance. The only thing it can do is break apart. Break it apart into its elements. Just look at that and say, okay, what are the elements that make it up? Well, cesium, Cs, and oxygen. Do not transfer the subscripts over. The only time you move the subscripts over is if it's a polyatomic ion. Neither one of these are polyatomics. But you do pay attention to diatomics. So if it is one of Bron H. Cliff, it gets that 2 subscript. Oxygen, when it's by itself, is O2 because it's diatomic. So the oxygen that's in the air right now is O2, not just O. Those are your decomposition reactions. You take one thing, you break it up. Right? Break it up into its elements. Then part G and H, this is where we get into using the reference documents that we have. So part G is a single replacement reaction. So for single replacement, I'm just trying to write kind of these reminders over here. We switch 2 elements. So single replacement, we switch 2 elements. You have a single element, and you have an element in a compound. Remember, the single must be more active. So whatever is single must be more active. So that's when we look at that activity series. And we'll look at this as we do an example. When you form something new, don't forget to look at charges. So make sure you crisscross charges. Right, whenever you form a new compound, you're combining 2 new things, you always have to look at the charges. So if we take a look at 14, we're going to actually do 2 here. We're going to do 14 and 15. So if we take a look at 14, I know this is single replacement because I have a metal by itself. I have a single element, and then I have a full compound. Right? I have a metal and a polyatomic ion. Now, in a single replacement reaction, the zinc will replace the silver, right? The metals will switch places. But this is where that single one must be more active. So in order for this to work, zinc must be more active. If you say, how do we know the activity? This is where the very last page, remember the very last page of your packet has this activity series of metals. The front page is the activity series. The back of this page are the solubility rules that we're going to look at for double replacement. So with the activity series, you will be given this. You don't have to memorize this, right? You'll be given this. So you have to look and see. Up here's the most active. Right down at the bottom is the least active. So you're comparing, what are we comparing? Zinc and silver. So zinc and silver is all the way at the bottom. All right, second from the bottom. So is zinc higher up on the activity series than silver? Yeah, it's closer to the top, right? Zinc is more active. The higher up it is, the more active it is. So because zinc is the single one and is more active, this reaction will take place. In order for a single replacement reaction to occur, whatever single needs to be more active. So that means that zinc is essentially going to kick silver out. Zinc's going to come up and kick silver out. So silver is going to be on its own now, just Ag. Zinc is going to combine with NO3. NO3 is a polyatomic ion. So zinc is going to combine with NO3. When you form a new compound, look at charges. On our polyatomic ion list, we have the charge of zinc, +2, and we have the charge of nitrate, is NO3 -1. So when we look at this, zinc is +2, NO3 is -1. They're going to crisscross. Put NO3 in parentheses with a 2 down here. So since zinc was more active, it kicked silver out. Now silver's on its own. Now if we take a look at 15, let's look at this one as well. We have gold, Au is gold, K is potassium. So again, we have a metal by itself and we have a metal that's in a compound. If we look at that activity series list, all right, we look at the activity series, for this reaction to work, gold needs to be more active than potassium. If I take a look at this activity series, gold is the least active. So since gold is the least active, gold, right, we can think about it this way, gold is lazy. Doesn't want to do anything. So if it's by itself and doesn't want to do anything, it's going to stay like this. We're going to write NR for no reaction. So if the one by itself is not more active, we just write NR. Okay, so the last type of example that we're going to look at is a double replacement reaction. We're just going to look at one of these together, and then there'll be some time to practice. So for double replacement reaction, just a reminder of what double replacement reactions are. We have two positive ions, right? Typically these are metals, switch places. Two positive ions that are in compounds will switch places. Now again, crisscross charges when you form something new, everything that we've been talking about. So if we take a look at 18, if you say, how do I know that this is double replacement? When you have two full compounds, two full ionic compounds, that tells us that it's double replacement. Now what happens here, and I like underlining the metals that are at the beginning. So we have Ag, which is silver, and Al for aluminum. In a double replacement reaction, we just switch the two metals. So we're just going to switch the two metals, which means Ag will combine with Cl. Your metal always comes first, right? Ag is going to combine with Cl, and aluminum will combine with sulfate, SO4. So Ag is going to combine with Cl, Al is going to combine with SO4. The two metals just switch places. Now if you put AlSO4 first and then AgCl, that's fine. But when you form something new, you always have to check the charges. Silver is a transition metal. Right? Silver falls right in the dip of the periodic table. So if we look at our transition metal list, silver's +1. So above silver, I'm going to put +1. Cl, it's a halogen, it's -1. Okay, so +1, -1, that cancels out. It's just AgCl. Then we have aluminum and sulfate. So again, periodic table, aluminum, +3. Right, +3. Sulfate, SO4. That's a polyatomic ion. SO4 is -2. So since SO4 is -2, you crisscross the charges. The 2 comes down after the aluminum. I'll put SO4 in parentheses with a 3 on the outside. Now we're just going to assume, right, we'll make a note here, we're going to assume that double replacement reactions work. So assume that reactions work. So that means that we won't have any no reactions for the double replacement. In order for a double replacement reaction to work, we usually need to form a solid. But we're just going to assume that they all work. So when it says write NR, don't worry about that for double replacement. We'll just assume that they all work like normal.